1. Introduction to air conditioning. Air conditioning is more than just cooling a space. It is the process of treating air in an enclosed area to control its temperature, humidity, purity, and movement for the purpose of maintaining comfortable and healthy indoor environments. While refrigeration focuses primarily on lowering temperature for storage or preservation, air conditioning serves people and processes by ensuring thermal comfort and adequate air quality. In this module, we will move from the fundamentals of indoor environmental conditions to the complete design and load calculation of an air conditioning system, including how to plan ventilation for buildings. 2. Indoor and outdoor air conditions. The performance of an air conditioning system depends heavily on the properties of both indoor and outdoor air. Outdoor air temperature, humidity, and pollutant content can vary dramatically with the seasons, location, and time of day. Hot, humid outdoor air places a heavier load on an air conditioning system, requiring more cooling and dehumidification. Indoor air is a mixture of conditioned air recirculated from the space and fresh outdoor air brought in for ventilation. Its properties depend on occupant activities, equipment, and the design of the ventilation system. While both matter, outdoor air represents the load on the system from the environment, while indoor air quality represents the comfort and health requirements of the occupants. The air conditioning system must be designed to balance these two. 3. Comfort conditions and comfort zone. The comfort zone is a range of temperature and humidity that most people find comfortable for daily activities. Human comfort is influenced by temperature. Too hot or too cold can cause discomfort. Humidity. High humidity can make a space feel stuffy, while low humidity can cause dryness. Air movement. Proper airflow enhances comfort by aiding evaporative cooling from the skin. Radiant temperature. The average temperature of surrounding surfaces also affects comfort. Personal factors. Clothing and physical activity can shift a person's comfort range. The comfort zone is typically maintained between moderate temperatures and relative humidity levels that prevent mold growth, excessive dryness, and thermal discomfort. 4. Indoor air quality, IAQ. Indoor air quality refers to the chemical, physical, and biological characteristics of air inside buildings. Poor IAQ can lead to health problems such as headaches, allergies, or respiratory issues. Major factors affecting IAQ. Contaminants from outside, pollution, dust, pollen. Indoor sources, furniture emissions, cleaning chemicals, office equipment. Moisture, leading to mold or bacterial growth. Ventilation rate, amount of fresh air introduced. Maintaining good IAQ involves adequate ventilation, proper filtration, humidity control, source control, reducing pollutant emissions indoors. 5. Psychrometry in air conditioning. Psychrometry is the study of the thermodynamic properties of air-water vapor mixtures. In air conditioning, psychrometry is used to determine how to modify air to meet desired indoor conditions. Key descriptive concepts. Dry bulb temperature, DBT, the air temperature measured without considering humidity. Wet bulb temperature, WBT, temperature measured considering evaporative cooling effect. Relative humidity, RH, the ratio of actual water vapor in the air to the maximum it can hold at that temperature. Dew point temperature, the temperature at which moisture begins to condense from the air. Using a psychrometric chart, engineers can visualize air properties and determine how much cooling or heating is required. How to dehumidify or humidify air. The changes in air properties after passing through coils or mixing with other air streams. 6. Central air conditioning systems. A central air conditioning system treats air at a central location and distributes it throughout a building. Essential components. Water chiller, cools water, which is then circulated to cooling coils. Water heater, provides hot water for heating coils. Air handling unit, AHU, contains fans, filters, coils, and controls for air treatment. Chilled water and hot water recirculation systems, loop systems that move conditioned water between the chiller/heater and the AHUs. Return terminals allow air to flow back from rooms into the duct system. Diffusers and grills distribute conditioned air into rooms and ensure good air mixing. CFM rating and tons of air conditioning. CFM, cubic feet per minute, measures the volume of air moved by the system. Tons of air conditioning describe cooling capacity, with 1 ton equivalent to the amount of heat needed to melt a certain mass of ice in 24 hours. 7. Load calculation and system design. The design of an air conditioning system begins with calculating the cooling and heating loads. Cooling load factors. Solar heat gained through windows. Heat generated by occupants. Heat from lighting and equipment. Infiltration of outdoor air. Ventilation requirements. Heating load factors. Heat loss through walls, windows, and roofs. Infiltration of cold air. Duct sizing and piping design principles. Ducts must be sized to deliver the required airflow without excessive resistance. Piping for chilled and hot water systems must minimize heat loss or gain. Pump and fan selection. Pumps circulate chilled or hot water. Fans move air through ducts, filters, and coils. 8. Air ventilation systems. Ventilation is essential for replacing stale indoor air with fresh outdoor air. There are 2 main categories. Natural ventilation uses windows, vents, and natural pressure differences. Mechanical ventilation uses fans and ducts to control airflow. Calculating fresh air supply for multi-story buildings. While the exact formula is not used here, the principle involves determining the number of occupants, considering activity level, ensuring enough fresh air per person to dilute pollutants, air handling for untreated fresh air. Fresh air is often untreated when first brought into the system, then filtered and conditioned before mixing with recirculated air. Forced convection-based ventilator design uses mechanical fans to create controlled air movement. Ensures even distribution and prevents stagnant air pockets. 9. Conclusion of Module 2. This module has connected the dots from comfort conditions and air quality to the design, calculation, and operation of complete air conditioning systems. In practice, these principles ensure that buildings are not only comfortable but also healthy, energy efficient, and adaptable to environmental changes.